Hi guys, this is Mrs. Valletta. After today's little lecture, I decided to go ahead and make you a quick little video. Hopefully this will help you with thinking about projectiles. I'm going to start with a drawing. This is the velocity, the initial velocity of my projectile, and I know the angle that my projectile was launched from the horizon. And what we're going to do today is try to derive the range formula. Remember, the range is the horizontal distance that the projectile travels. That assumes that it comes to the same height when it lands. That's this range. Obviously, if this was to go over a cliff and continue, you'd have to do the second part of the formula, including all of this position here. But for today, we're going to pretend that it lands at the same height. And so let's start with what we know in the x position. So if you want to know what the object travels in the x direction, the easy thing to do is to think about the fact that in the x direction, it has inertia and that there are no unbalanced forces acting on the object. And so we can simply come in and put in our rearranged constant velocity formula where the velocity in the x direction is equal to time. Now, how do we find the velocity in the x direction? Well, that's where we have to come back and disaggregate our vectors. And remember, this is the adjacent vector. So the velocity in the x direction then is equal to the initial velocity times the cosine of theta. That's our launch angle. And time, you guys, the time that it's in the air, we call that time the hang time. And that's twice the amount of time to go to the top of the projectile as to come down. And so don't forget to think about the fact that it's 2 times the time. That's the hang time. And so again, if we want to know the range then is just equal to, we can substitute in, whoops, that pen died. We can substitute in our velocity x, so that's v naught cosine theta for the hang time. That's time. Okay, that's what we can do on that side of the equation. So now let's look in the y direction and try to decide what we can figure out there. So let's write down our variables about what we know. So again, y naught, yf, v naught in the y direction, v naught in the, v final, excuse me, in the y direction, a and time. And we don't know the time yet. We do know acceleration, and that's equal to negative g, which we know is negative 10 meters per second squared. Do we know the initial position? Yeah, we know the initial position is 0, and we know the final position is 0. The initial velocity, well, we can go back to our drawing and we can disaggregate the vectors. So if we go back here and let's think about this, remember this is the opposite side. And so for us to find the component in the opposite side, it's the velocity in the y direction, right? And using trigonometry, we know then that that is the sine of theta. So our velocity in the y direction is v naught sine theta. How about the final velocity? Well, from work that we've done before in free fall, we know that the velocity on the way up is exactly equal to the velocity on the way down, but it's equal but opposite. So this Vy final is equal to the negative of the initial y velocity. And so we're going to write that there as negative V naught sine theta. All right. And I think that's all we know right now. Now, in class, I used the second kinematics equation to derive the formula, but for this video, I'm going to show you a way to use the first kinematics equation to derive the formula, because you can use either one. And I'll remind you that the first kinematic equation is even easier. That is, the velocity final equals velocity initial plus at, right? And those are in the y directions. And so let's use what we have to see it and substitute in there. Oh, so we'll do it down here. So velocity final in the y direction, well, that's negative v naught sine theta is equal to velocity initial, which is v naught sine theta, plus the acceleration, well, that's a negative g, right, times time. And again, what are we missing over here? Well, we're missing time, so we're going to rearrange this formula for time. All right, so let's move both of these on the other side. So that's negative 2 v naught sine theta equals negative gt. So then t equals 2 v naught sine theta over g, because the negatives cancel. All right, so let's take this and substitute it back into our equation. So we come back up here and we substitute in, and we have v naught cosine theta times 2 v naught sine theta over g, and that's equal to our range. And today I mentioned that you were supposed to learn this, but let's pretend that you didn't learn this. So 2 times cosine theta sine theta, so 2 times cosine theta sine theta is considered the double angle formula, and so that's equal to sine 2 theta. So we can substitute that in, and these are squared, so we get v naught squared times sine, 2 theta, almost made a mistake there, theta over g, and that's our range formula. Now, does this formula make sense to us? Well, it should in some ways. If you look here, 2 times theta, well, we already know that the best angle to launch is 45 degrees. So 2 times theta is equal to 90 degrees, and the sine of 90 is equal to 1. So that's obviously going to give us our best range. The greatest sine is going to give us our best range. The other thing that you have to think about is that you have, it's v squared because you have the time up and the time down, right? So its hang time is in both directions, and so you need to square the velocity. Hopefully that's going to help you. Now, when I talked about the extra credit for the lab, let's go back and think about this. You have the range, right? And from the range, so you have this range, and you have the time, you can easily get the velocity in the x direction. Once you have the velocity in the x direction, it's a simple matter of trigonometry to get the launch velocity, and when you get the launch velocity, you can get the y velocity. I want you to get both of those and then reconfirm using the range formula, the one that you've derived. Okay, that using those velocities you would get the range that you measured in your lab. I hope that helps you do your lab. Let me know if there are any questions. Thanks.